Here we're going to talk about general trends in chemical properties. So before we had talked about elements in the same group tend to have similar chemical properties, and further learning that that's because they have similar valence electron configurations. This is generally true, but not always true. And this is true more so for main group elements than they are for transition metals. And so we need to be a little bit careful with that. So we'll look a little bit more specifically at that. There's kind of another interesting aspect to this, and chemists have known about it for a long time, but the first the first member of each group is quite different than the rest of the members of the same group. So lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine all act a little bit differently than everything below it. This is mainly due to its size. It's pretty small in comparison. So we're just going to look through the periodic table pretty briefly here and look at these different groups. So hydrogen, there's really no good spot for hydrogen. It really belongs in a group all by itself. That's why we put it up in the upper left-hand corner. It's pretty bizarre just because it has only one electron and one proton typically. But the rest of the alkali metals, which is group 1A, so that's NS1, you have lithium, sodium, potassium, rubidium, and cesium. These are actually metals. They're called alkali metals. We don't normally think of these as metals like sodium or potassium. We think of them as their +1 cation. They all very much so prefer to be a +1 cation now, as we know, because they can lose their outermost S1 electron, their one valence electron, to become a noble gas configuration. Most of these metals will do this very aggressively. So sodium metal is used fairly commonly in a chemistry lab, but when it gets exposed too much to moisture, it can actually start a sodium metal fire. So it's explosive enough in trying to get rid of that electron that it can be very, very reactive. And that's actually why you see, and it gets more reactive as you go down that group. So you see potassium is sealed, same with rubidium and cesium. This is to prevent it from coming in contact with oxygen and moisture, which is enough to set it on fire. So you can actually look up some YouTube videos of sodium metal being tossed into a lake or something, and it essentially explodes because of that really, really fast reaction. In the past, especially, sodium metal was one of the biggest causes of fire in a chemistry lab. So what would happen is people would wipe up something maybe with a paper towel, and if it had some sodium metal in it that was being used for an experiment, that would dry out and then start a fire. But it was when no one was around, maybe in the middle of the night or something like that, like a trash can fire or a fire in the sink. So you have to be very careful dealing with sodium metal. But again, that's because it's very different than sodium Na+, which is what we're more familiar with. So going from the alkali metals to the alkaline earth metals, these are also metals, of course. Beryllium, magnesium, calcium, strontium, and barium. Magnesium metal strips you might be familiar with already. And here there's some calcium. We often don't think about these in terms of them being metals, but they are, just like sodium and all of that. They are also somewhat reactive, but not nearly as reactive as alkali metals in terms of their reactivity with things like water. But they do, generally the way we interact with these metals are in terms of them as their cations. So magnesium 2+ is a common cation that we experience all the time. Calcium 2+, same sort of thing, and that's what we're more familiar with them as. But they'd all have fairly similar properties. All right, group 3A. So here we skip the whole transition metals, since that does not have the same sort of group characteristics that we expect from main group elements. And we do have some big similarities. Aluminum, gallium, and indium tend to all be +3 charges associated with them in general. And there are some pretty large similarities between aluminum and gallium and indium. Again, boron was a little bit different just because it is so much smaller than the others. Group 4A is carbon and silicon. But then things start getting a little different just because at this point we're now transitioning through the metalloids into metals, going down. I don't think you probably wouldn't have thought that carbon has some similarities with something like lead or tin. But based on these characteristics, we would expect there to be some similarities, but there may not be quite as many because of that transition between a metal and between metals and nonmetals. Same thing can kind of be said here, where you have nitrogen, which again is very different. You have phosphorus and a couple different types of phosphorus that are actually around: arsenic, antimony, bismuth. Oxygen and sulfur can have some big similarities, and notably that they're both 2- charges. And then again, you have this transition to something more metalloid-like or metallic, like tellurium. Then we have halogens. We're somewhat familiar with halogens already. We've been dealing with some halogens. Fluorine gas, chlorine gas, bromine liquid, and iodine is a solid, but they all do tend to prefer that -1 charge. So there are quite a few similarities between these halogens, and they all are diatomic in nature. It's just iodine tends to be a solid at room temperature, where bromine's a liquid at room temperature. Chlorine and fluorine are both gases at room temperature. Then lastly, the noble gases. These are all gases that are very inert. They do not react much at all, and that's because they're neutrally charged and they already have a filled s and p orbital. So all of those orbitals are filled. So it already has a noble gas electron configuration, so there's no need to form an ion or anything like that. And these are some that you can, since they're a gas, a common thing that can be done with them, like neon signs, as you know, run electricity through the gas since it's inert to excite electrons. Upon the relaxation of those electrons, you emit photons, and that's where you get those distinct colors associated with these elements.